Okay, so let's do that. Let's prove that the heat capacity at constant pressure is larger than zero. And to do that, what we're going to use is the generalized Myers relation, which we had seen already before in the previous lecture, uh, in the case of the ideal gas, and also in the case of the general case, which is this one. Cp minus Cv equals V times T alpha squared and the isothermal compressibility. Okay. So what we're going to do next is, first of all, we're going to show that the heat capacity at constant volume is always positive, and then we are going to show that the isothermal compressibility is always necessarily positive. So these two things together imply that not only the heat capacity at constant volume is larger than zero, but also that the heat capacity at constant pressure is always larger than the heat capacity at constant volume. Okay, because in the right hand side here, which is the difference between the two, that is a positive number because the volume is positive, the absolute temperature is positive, this guy is squared, and the only thing that could make this negative is actually this beta t, which is positive. Okay. So this is what we are going to prove, and what we're really interested in establishing is that this is larger than zero. Okay, so let's start, and to begin with, we are going to think of a thermodynamic system that is mechanically and thermally insulated from the outside. Okay, so we had already seen this when we started talking about the principle of maximum entropy, okay, in the entropy chapter. So let me just draw some adiabatic rigid walls for my system. And the system, well, we know what happens with such system, right? So we know that ds is larger or equal than zero in this case, because of the adiabatic insulation, which means that the entropy can only grow in a system like this. And if you are already in a state of maximum entropy in such a mechanically and thermally insulated system, so we are saying this is constant, the internal energy, and also the volume is constant. Okay, volume is constant means there's no mechanical work, and implying that the internal energy is constant means also that there's no heat coming in or out, which is precisely the situation we have in mind. Okay, so in these two constraints, the state of maximum entropy is stable, because if you are already at maximum entropy, no virtual process will take you out of it, because if it would take you out of it, if you are already at maximum entropy and you are allowed to go to some other state, your entropy would go down, and this is not allowed by Clausius theorem. Okay, so this just to remember the principle of maximum entropy. And what I'm going to say here is that the total volume of my system is actually going to be 2V, and the total energy of my system is 2U. Okay, so this is a very ingenious proof, actually, it's in the book of Herbert Cullen, in the more modern editions, and it's really cool. You will see in a moment. So what we're going to do is we're going to divide the system with some imaginary wall, okay, into equal parts. So you have to imagine these are equal parts, which is more like this, or even more like that. Well, I don't know, there. So the thing is that this part here has volume V and internal energy U, and this part here is identical. We start from the assumption that the system is already at a stable state. Okay, so the system as a whole has the maximum possible entropy. Okay, and then we're going to imagine process, virtual process. It's a made-up process that cannot happen in reality, by which, let's say that the left-hand side of your system absorbs a little bit of heat, and this heat, this energy, in this case heat, is going to be coming from the other half of the system. Okay, so that the total energy is conserved, and the only thing is that it's redistributed in a way that makes the system non-homogeneous in the end. Okay, So what the notation here means is this negated or bar d. It denotes a virtual process. I could have written d if you want, okay, and most books also do that. The thing is that this process that I'm highlighting like this, it's a made-up process, so it's just a calculation tool. Such process cannot exist, okay? So that's why I call it virtual process. It doesn't matter, okay? You can just think of a differential. That's what I really mean. There is an infinitesimal amount of energy that this system on the right-hand side is given to the system in the left-hand side. That's all, okay? In the lecture notes, I use another notation, some sort of very fancy calligraphic little d, which I cannot do by hand. So you have it there. It's just to be consistent. So this thing is the differential of a function of state. This thing is an infinitesimal change in a process variable, and we needed a third symbol to represent these virtual things, which I'm going to use this. Okay. So first of all, before this process happened, okay, what was the entropy of my system? Well, the entropy, assuming that it is additive, it was S of 2u and 2v. Because remember that the natural variables of entropy are internal energy and volume, okay? And because I'm assuming additivity, this is equal to twice the entropy at u and v. So the entropy of any of the two systems initially. And then in the end, what I have for the total entropy is the entropy of the left-hand side thing, which is u plus du, and the volume is unchanged. And here is plus S of u minus du v, okay? And I know that because initially I was already in a stable state, I know that this entropy on the right-hand side is the maximum possible entropy. Any other state, including this non-homogeneous state here, will have less entropy, okay? So this is what I have, actually less, really less entropy. Okay, so this is something I know, and I will exploit this now. There is a smart trick here, which is taken from the book by Herbert Cullen. It's actually quite ingenious. You can use here the definition of the finite difference approximation, or if you like, the finite difference approximation to the second derivative, okay? And this, if you have any function, right, so a function of x, the derivative of the function with respect to the variable, the second derivative, you can approximate it as the function evaluated at x plus h minus twice the function at x, and then plus the function at, well, let me just write it up here. We'll try to make it smaller somehow, like this, plus the function at x minus h, everything divided by h squared, okay? In the limit where h is very small, the right hand side here is a good approximation to the second derivative, okay? And it becomes exact in the limit of h going to 0. And here you see we have something very similar, okay? So if we take this thing to the right hand side, we will end up having s u plus this du v minus twice s of u and b, and then plus s of u minus du v. And we know that this would be then smaller than 0, okay? Or if you like, smaller or equal, okay? Let's just write it like this. So if this is the case, what I'm saying is, in the limit that this is really infinitesimal, what I'm saying is that the second derivative of s with respect to u squared at a constant volume, if you like, this thing is smaller or equal than 0, okay? But now remember what was the differential form or the fundamental thermodynamic relationship in terms of entropy. You have 1 over t du plus p over t dv, okay? So the natural variables are u and v, and the corresponding conjugate variables are 1 over t and p over t. which means that the partial derivative of s with respect to u is this thing here, 1 over t. So the partial derivative, second partial derivative of s with respect to u twice equals the partial derivative of 1 over t with respect to u at constant v. Okay, and if we carry out the derivative, you get 1 over t squared with a minus sign, and here you have the derivative of t with respect to u at constant volume. Okay, and what is this derivative? Well, that is we can put the internal energy in the numerator, because that's what we have learned that we have to do to reduce such derivative. And this, with respect to t at constant v, it's very badly written, let me put it better, u divided by t at constant v to the minus 1, and then this equals 1 over t squared, and here you have tds minus pdv, and here in the denominator you have dt, the whole thing evaluated at constant volume. What you get in the end is minus 1 over t squared of the heat capacity at constant volume, and this because it has a dv and v is kept constant, this goes to 0, so what you get is this. Okay, by definition, t partial derivative of s with respect to t at constant volume is the heat capacity at constant volume, and we know this thing is smaller or equal than 0. Okay, so what this means is that the heat capacity at constant well, let's just I forgot one thing here, sorry, I forgot that the whole thing was to the minus 1. Okay, so you see that this whole expression here is evaluated to the minus 1. So what you get here really is the prefactor, right? And then the heat capacity at constant volume is really in the denominator. Okay, but anyway, it doesn't matter. The absolute thermodynamic temperature is positive and is squared on top of everything, which means that if this number is going to be negative in general, then it means that the heat capacity at constant volume is necessarily a positive number, or if you like, larger or equal than 0. From the beginning, we could have said this was just strictly smaller, okay, which I think is actually better to do. So what you get is that the heat capacity at constant volume is larger than 0. Okay, so that's our first proof. And then we need to make the second part of the proof, which is that the isothermal compressibility is always a positive thing. So for that, we are going to resort to the free energy. Okay, so that is a more appropriate potential for what we want to do. And the system now that I have in mind is well, it's very similar but different in only one way, which is that the walls now of my system are not going to be they're still going to be rigid, so that the total volume is going to remain constant, but the walls are going to be diathermal, and in fact I want to put here a heat bath, okay, at temperature T, which is in contact with the whole system. Okay, and just like before, I'm going to take the available volume and I'm going to break it into 2 equal pieces. Okay, so I'm assuming that initially in this configuration in which I am indeed in contact with the heat source, I'm going to say my system is in a stable thermodynamic equilibrium state. And again, well, this bit here on the left will have temperature T, and we'll have volume V, and on the other side, because I'm in equilibrium, I have the same temperature and the same volume in this case, because I'm splitting the system into 2 halves. Okay, fine. So let's imagine now that there is a imaginary process in which this wall here, which is purely imaginary, there's no real wall here. Okay, but what I'm going to do is I'm going to move it a little bit to the right. Okay, so that the left-hand side system is expanding and it's expanding at the expense of the right-hand side system contracting, because we know that the total volume has to be kept constant. Okay, so what we have? So just like we did before, the free energy, we know this from the principle of minimum free energy that we studied in the previous lecture. If you are in a thermodynamic system which is in thermal contact with a heat source at temperature T, then if you are in a stable state, then your Helmholtz free energy F needs to be minimal. Okay, so what we know is that in the initial state in which you have temperature T and volume 2V, this function is the minimum possible value it can have. Okay, and we also assume that this is going to be additive. This follows from the additivity of energy and entropy. So this is going to be twice F of T and V. Why am I writing T and V? Because remember that the natural variables of the Helmholtz free energy are temperature and volume. Okay. Okay, so then what happens when the volume is pushed? It's increased a little bit on the left and decreased a little bit on the right. Well, what happens is that the free energy is going to be the sum of the free energy of the right-hand side part and the free energy of the left-hand side part. Okay. And because I know that initially my system was in a stable configuration, the right-hand side is necessarily smaller than the left-hand side. Okay, so this is going to happen simply because I'm saying that my system was initially in a stable thermodynamic state. Okay, so again, using the same argument of the finite difference that we saw before, what we conclude from this inequality is that the second derivative of F with respect to the volume squared at constant temperature is going to be larger than 0. Okay, and once again, remembering what the fundamental thermodynamic relationship is in terms of the Helmholtz free energy, that is S dT minus PdV, we see that the partial derivative of F with respect to B is minus P. Okay, so what we have here is minus the partial derivative of P with respect to V at constant T. Okay, and this thing, just remember also that the isothermal compressibility is going to be equal to minus 1 over the volume, and the partial derivative of the volume with respect to the pressure at constant temperature. That's the definition of it. So what we have here is just 1 over beta T times the volume. That's what we have. And we know that this is larger than 0. So once again, the volume is larger than 0 already, which simply means that beta T is larger than 0. Okay? So we have proven that beta T is larger than 0, that Cv is larger than 0, and therefore this implies that Cp is larger than 0, which is what we want. Because this implies that the Joule-Thomson coefficient that we had defined before, and I now forget what it was, let me just copy it from somewhere here, this volume divided by heat capacity at constant pressure, T alpha minus 1. Okay, so this thing is boring and always positive, which means that the sign, the whole point, is decided by this parenthesis here. So T alpha has to be larger or equal than 1 for the Joule-Thomson coefficient to not be negative. Okay, so now we're ready to explore, if you like, a little bit more in practice what you have to do if you want to take gas and cool it down using the Joule-Thomson effect as to a temperature which is as low as possible.